Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions from May June 2023, Paper 1, Variant 2. In the last two videos, we have already discussed from question 1 to question 20, and today's lesson, we will start from question 21. In this lesson, our main focus will be on waves, and also we will discuss some questions from electricity as well. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of these contents, and also you can have better understanding of these questions. Let's study together. Let's improve together. Question 21 says a longitudinal wave is traveling from left to right. The graph shows the variation of the displacements of the particles with distance along the wave at one instant in time. Displacements to the right are taken as positive and displacements to the left are taken as negative. Which labeled point represents a compression? So first of all, we need to understand what is compression and what is rarefaction. Compression simply is a region where particles are moving towards each other. Compression means particles are moving towards each other. That region we will call is compression. And rarefaction is just opposite. Rarefaction is just opposite of compression. So we can write down rarefaction. Rarefaction is a region where particles are moving away, means they are moving away from each other, and that region we call is rarefaction. Now if you have understanding of these points, simply you need to read the graph and you can find compression. If you look at this point here, so if we look here, displacement is positive, this displacement is also positive. It means these particles, they are moving to the right. So this particle is moving to the right, this particle is also moving to the right. So this is not compression and also this is not rarefaction. Now if you look at point B, we can choose 2 points. Here we have one particle, this one has positive displacement, means this particle is moving to the right, and if we take another particle here, this particle is moving to the left because its displacement is negative. It means this one is compression. So B, here we have compression, so we can say this is compression. So this is compression. Now if you look at point D now here, so we can also try to find out, is it compression or rarefaction? So here we have displacement positive, means particle is moving to the right, and here we have displacement negative, means particle is moving to the left. So it simply means that here we have rarefaction. So here we have rarefaction. Question was asking us to label the point that represents a compression. So the answer for this question has to be B. So B is the right answer. So this is a beautiful way how you can approach this type of problems, and this question is a repeated question. You will see this question in many past papers. Question 22 says a source X emits a sound wave of constant frequency F. The wave is subsequently received at a stationary detector Y. The frequency of the wave that is detected by Y is less than F. What could be the reason for this? So this is pretty straightforward question. This is due to Doppler effect. Due to Doppler effect, and it is given to us that observed frequency, in this case observed frequency, this is less than emitted frequency. So it means that source is moving away. Source is moving away. So pretty straightforward question. So we can simply say in this case source is moving away because listener is at rest. Listener is at rest. So the answer for this one has to be C. If you look at option A, between X and Y, wave undergoes diffraction. When waves diffract, frequency does not change. Frequency remains constant. So this is wrong. Wave undergoes reflection. When waves reflect, frequency also does not change. X is moving towards, in this case, F observe. This will be greater than F. It means source is approaching. So these points you need to understand. Maybe they can ask you questions about this next time. Question 23 says a beam of visible light is in a vacuum. What could be the frequency of the light? So simply we need to calculate frequency of visible light, and for visible light we need to understand the range of wavelength. This is what they are expecting you to remember. The wavelength of visible light. Wavelength of visible light is about 400 to 700 nanometers. We need to calculate frequency. So frequency simply will be equal to speed of light divided by the wavelength of visible light, and speed of light in vacuum is about 3 times 10 to 8 meters per second divided by wavelength, and we have the range of wavelength. You can use any value. You can use the minimum value, you can use the maximum value. Your result will be almost same. There will be not a big difference, because we can see here we have this is 10 to 11, this is 10 to 14, 1000 times greater. Here you can see this is 10 to 5, this is 10 to 8, 1000 times difference. So it will not make a big difference. So we can take a average value around 600 nanometers. So it means 600 times 10 to minus 9. Now if we simplify this one, we can write down 3 times 10 to 8 divided by, we have 600, we can say 6 times 10 to 2 times we have 10 to negative 9. So if we further simplify, we can say this is 3 times 10 to 8 divided by, we have 6 times 10 to negative 7. So we can say this is equal to about 0.5. This is 3, we can cancel with 6, we have 2, 1 divided by 2 we'll get 0.5, and here we will get this is 10 to 15. So in this case we will get 5.0 times 10 to 14 hertz. So the answer for this question has to be D. Question 24 says a vertically polarized beam of light of intensity I0 is incident normally on a polarizing filter. The transmission axis of the filter is at 45 degrees to the vertical. The beam of light transmitted by this filter is then incident normally on a second filter. The transmission axis of the second filter is horizontal. What is the intensity of the beam of light after transmission through the second filter? So here we have I0, and this light is vertically polarized, and we can say I1 after first filter, and we can say intensity of light I2 after second filter. So for this question we need to find out what is value of I2. First of all, let's try to calculate I1. So simply we need to use Malice's law, means I transmitted. This one has to be equal to I incident times cosine square theta. Cosine square theta. Now in this case we have, first of all, vertically polarized light. So we have vertically polarized light. So this is vertically polarized light, and the angle between vertically polarized light and transmission axis is 45 degrees. So we have angle 45 degrees. So we can also draw here, so you can see the angle between transmission axis and vertically polarized light is 45. So simply we have to use 45 degrees here. So in this case we can write down I0, we have cosine of 45 square, and cosine of 45 is 1 over root of 2 square. So it simply means that we have I0 times 1 by 2. So this is value of I1. Now we need to find out I2. I2 has to be equal to I1 times cosine square of theta, the angle between incident light and transmission axis of second filter. Now this is a little bit tricky one. Now you need to understand this light, this component of the light, it will be transmitted. So we can draw this component here. So we have this component of incident light. So this is our incident light now, and our transmission axis is horizontal. So the angle between these two, angle between this incident light and transmission axis, again this angle is 45 degrees. So simply we can rewrite here I2, this one has to be equal to I1 times cos of 45. So this is cos of 45 square of this one. So here we have I1 cos of 45. This is 1 over root of 2 square. So again we will get this is I1 times 1 by 2. So we can write on here we have I2. This is equal to I1 times 1 by 2. But value of I1 we have here. So this is I1 and this is I0. We can replace I1 with I0. So we have this is I0 times 1 by 2 and this is multiplied by 1 by 2. So we have here 1 by 2. So if we solve this one, we will get I0 times 1 by 4. So the answer for this question has to be B, and this is the way how we approach polarization questions. If this is clear to you, it means you can answer a lot of questions from polarization at this level. And if it is not clear to you when you watch this video one time, you can stop the video, you can do question again by yourself and watch video again. And this question will make your polarization concept very clear. Question 25 says a stationary wave is formed by two progressive waves traveling in opposite directions along the same line of travel. Which statement about the two progressive waves is not correct? For a stationary wave to be formed, two progressive waves, they should have the same frequency, they must have the same wavelength, and also they must travel at the same speed. It also means that same type of waves, same type of waves means sound waves. They can form stationary wave with sound waves, but sound waves cannot form stationary waves with light waves. So the same type of waves, they must have constant phase difference. This is incorrect. This is not condition for stationary waves to be formed. So the answer for this question is A. We need to find out which statement is incorrect. Question 26 says the sound from a loudspeaker placed above a tube causes resonance of the air in the tube. A stationary wave is formed with two nodes and two antinodes as shown in the figure. Tube has height 60 centimeters and speed of the sound in the air is 340 meters per second. What is the frequency of the sound? So this is a typical type of question. You will see this question in many past papers. So this is a repeated question. You need to master how to approach this type of questions. So for this question, it is given to us, we have node here at this end, and here we have antinode. Here we have node, means at this point we have node, and at this end we have an antinode. Now we need to understand the distance between one node and one antinode, consecutive node and antinode. This distance is equal to lambda by 4. So the distance between next antinode and node is also lambda by 4, and this distance also has to be equal to lambda by 4. So in this case we have L, that is equal to 3 lambda by 4. So from here we can find out value of lambda. Lambda will be equal to 4L divided by 3, and value of L is given to us, that is equal to 60 centimeters. So 60 times 10 to minus 2, 10 to minus 2, or simply we can say this is 4 over 3 times 0.6. So this is value of lambda. Now we need to find out frequency, and frequency simply will be equal to V divided by lambda. Now we just need to plug in values and we can calculate value of frequency. Speed of sound is given, that is equal to 340. We have to divide by this. So we have 4 times 0.6 divided by 3. So we can simplify, we can say this is 340 multiply by 3 divided by 4 times 0.6. Now if we solve this one, our final answer up to 2SF has to be equal to 430 Hertz. So this is the final answer. So this is value of frequency. So the answer for this question has to be A. Question 27 says a continuous progressive water wave in a ripple tank passes through a gap in a barrier and diffracts. The width of the gap is greater than the wavelength of the wave, which change causes the wave to spread over a large angle as it passes through the gap. Large angle simply means that more diffraction. So how we can increase diffraction? So simply we can say large angle means more diffraction. More diffraction. So if gap size, this gap size, in the question it is given to us, gap size is larger than wavelength of the wave, so it means there will be less diffraction, or we can say little diffraction in this case, less diffraction. So how we can increase diffraction means how we can make more diffraction. So how we can increase diffraction? So this is what we need to answer. More diffraction can be if we reduce the gap size. So we have two options. One, we can reduce gap size. We can reduce gap size. And the second option we can increase the wavelength. So we have these two options. If you look at given options, it is given to us a small decrease in the wavelength. This will make diffraction even smaller. So in this case, diffraction decrease. So we will say diffraction will go down, means there will be less diffraction. So this is not possible answer. A small decrease in the width of the gap means we reduce gap size. Yes, diffraction will increase. So this can be a possible answer. Small increase in the frequency of the wave. If frequency increase, wavelength will decrease. It means that there will be less diffraction. Small increase in the height of the barrier. Height of the barrier doesn't affect. Gap size only affect. So it means it will have no effect. So the answer for this question has to be B, a typical question and repeated question. Question 28 says the diagram shows a view from above of a double slit interference demonstration. L is a monochromatic light source with a vertical filament. B is a barrier with two narrow vertical slits. S is the screen upon which interference fringes form. The intensity is I at the point on the screen where the center of the fringe pattern forms. When one of the slits is covered, what is the intensity at the same point on the screen? So in this case, center maxima will form at this point, or we can say the center bright fringe. And center bright fringe is formed when the waves are coming from these two slits. So waves are coming from these two slits, and when these two waves meet at this point and they interfere constructively, a center maxima is formed. So we can imagine these are two waves, they meet at this point, they are in phase and they form a center maxima, mean the super wave, they will form this one. We can also imagine the amplitude of this wave, let's say is A, amplitude of this wave is A. So the amplitude of this wave has to be equal to 2A. But for the second case it is given to us, one of the slit is covered, means no waves are coming from one of the slits. So for the second case, now we have only one wave. So we can write down our second case here. At this point we are talking about it, so we can write down here. So we have only this one wave coming. So the center maxima also will have only amplitude A. So amplitude A, so here amplitude A. We have to compare the intensity. So for case 1 we can say we have I naught, this is equal to I in this case, means the intensity it is given to us is equal to I, and this has to be equal to K times A square, and A square we can write down simply this is A naught. And for the second case, we can say the intensity is I1. This intensity also has to be equal to K times A1 square. In this case, we can also write down that I1 over A naught square. A naught, we need to understand, this is equal to 2A. So we are talking about this one. This is equal to A naught. So this is 2A square. This one has to be equal to I1 divided by amplitude of this, means A square. Now from here we can find out I1. So if we write on here, we can say I1, this one has to be equal to I naught times A square divided by, this has to be 4 times A square. So we can cancel a square with a square. So I1, this is equal to I naught by 4, and it is given to us I naught is equal to I. So simply we got here, this is I divided by 4. So this is how you can answer this question. This question is also a typical question. You will see this one in other past papers as well. So what we have done in this case, let me repeat once again. So this is the amplitude of the resultant wave, means this A naught, this is the amplitude of this resultant wave, and intensity of this resultant wave is given to us, that is equal to I, and I has to be equal to K times amplitude square. So I1 also has to be equal to K times amplitude 1 square, A1 square, and amplitude of the second wave is A, so A1 is equal to A1 is equal to A. We can also write out here, we are talking about this is A1. So this is A1. Now simply we need to equate these two and we can find out I1. So our final answer for this question has to be D. Question 29 says green light of wavelength 550 nanometers is incident normally on a diffraction grating and produces a diffraction pattern on a screen placed 3.5 meters from the diffraction grating. The third order maximum on the screen is a distance of 4.75 meters from the zeroth order maximum. What is the distance between two adjacent slits in the diffraction grating? This question is about diffraction grating. So first thing you need to understand. And for diffraction grating, simply we can use d sine of theta. This is equal to n times lambda. For this question, we need to find out d. So we can say d, this one has to be equal to n times lambda divided by sine of theta. We have value of n, that is 3, and we have the wavelength. Wavelength is given to us, that is equal to 550 nanometers divided by sine of angle, but we don't have value of angle. So first of all, we need to find out value of angle. But for this question, we have this distance, we have also this distance, so we can find out value of this angle. So in this case, we can say tangent of theta, this will be equal to 0.75 divided by 3.5 meters. So if we solve this one from here, we can find out value of theta. So we have tangent inverse of 0.75 divided by 3.5. If we solve this one, we will get theta is equal to 12.09 degrees. So this is value of theta. Now simply we need to place this value here, and if we solve this one, we will get d is equal to 7.88 times 10 to minus 6 meters. So this is value of d. So the answer for this question has to be C, 7.9. So up to 2SF we can write down, this is 7.9 times 10 to minus 6 meters. So C is the answer. Question 30 says which charge can be carried by a charge carrier, and charge on any charge carrier has to be integral multiple of the charge on single electron. It simply means that n has to be integer number. Integer means it can be 1, it can be 2, it can be 3, 4, and so on. But 2.5, for example, 3.5, 3.6, 5.7 something, these are not possible. So these are not integers. And E is equal to 1.6 times 10 to minus 19 coulombs. So if you look at the first one, this is smaller than 1.6, so it means this is not possible. If you look at option B, we can find value of n. So we have 4.0 times 10 to minus 19 divided by 1.6 times 10 to minus 19. So we will get about 2.5. So this is not integer, so this is also not possible. If you look at option C, for option C, we have 4.8 times 10 to minus 19 divided by 1.6 times 10 to minus 19. In this case, we will get 3. So this one is possible. This is integer. If you look at option D, we can also calculate n. So we have 9.1 times 10 to minus 19 divided by 1.6 times 10 to minus 19. If we solve this one, we will get this is about 5.68. So this is also not integer. So this is also not possible. I hope this video was helpful and you have improved your understanding of waves, and also you have improved a little bit understanding of electricity as well. In tomorrow's lesson, we will discuss remaining 10 questions, and we will discuss a lot of questions about electricity and radioactivity. And next lesson will help you to improve your understanding of electricity and also radioactivity. And if this video was helpful, please like and subscribe, because your encouragement is very important. I'll see you in next video. And if you have any questions, please leave your questions in comments.